All right. Finally. Sorry about that. I want to do some conceptual work. First, just saying that I know we're moving through a lot of content. I'm very aware of that. I know a lot of this content is very new to us. I want to just get a fist to five, five being like, I'm very confident in everything we've covered so far, not a problem. Fist being like, I'm very lost in this class. I'm very worried about the midterm. Where are we at? Is that a 3? Okay. 3. The gentleman's 3. The Hamden City 3. 4. 3, 4. Okay. And then today I assigned a little intro text to a very famous textbook on such things for computer vision. I covered kind of high, medium, and low. And I want to get your kind of feedback. 5 was it was a very easy reading to get through. Fist was very difficult. Where are you at? 3, 2. Okay. The 2 was because the content was tough or the format of it wasn't interesting, too many citations. Walk me through it.
Yeah, it just felt like a lot of kind of definition stuff that I might have looked over and not really remembered as much.
Yeah, and there's
looked into too deeply.
I think that's absolutely true. Like, you're not wrong there at all. And in fact, until we get to the midterm, I'm throwing a lot of definitional content at you, right? After the midterm, once we do the oral exam and you start thinking through an individual project, the back half of the semester looks very much like we work as groups, we apply content. I'll bring a little bit of new content in as examples, but we're really like, we won't be covering too much stuff that is as rapid and fast at you as this is, because I have to bring you all the way up from like, what is AI in digital culture to like, this is how it works, right? So if you feel like things are going kind of at a white knuckle pace, they are, and it's just so you have that base level ability to look at these larger systems and have an inkling of what's going on. I use this parallel if you were like in an upper level English class and they were teaching you how to do close text analysis, right? And you're like, oh yeah, I know how to read, it's not a problem. And then you step in that classroom and then all of a sudden it's like, whoa, okay, we're reading way different, right? We might spend an entire class talking about like 2 paragraphs or even 2 sentences. It kind of deconstructs your ability to be like, oh, I know what reading is. That's kind of what I'm trying to do here. We're fluent in images, we're fluent in things like AI, or many of us use GPTs or stuff like that, but we don't often know what's going on behind the scenes. And in order to get there, there's a long history. I mean, it starts with like the human eye. It starts with the idea of qualia, and it moves all the way up to what we'll talk about today. This week is supposed to break down low, medium, and high vision systems. That doesn't mean that like low vision systems aren't as important as high vision or medium computer vision. It just means that they're more rudimentary, and they're found almost everywhere. There are a lot of slides here, and my plan is that we'll take about a week to go through the slide deck, and if we have extra time on Thursday, we'll do some debrief, kind of like we did last Thursday. Does that make sense? Please, the biggest thing you can be doing from my perspective for success in this class and participation is stopping by my office hours, shooting me a text or an email if you're encountering problems or you don't know exactly where you want to go with a project in this class. I think many of us might not know, and that is totally fine, but that's something I'd really like to workshop with you, right? Because if we can find something that you're interested in, and we can look at maybe sports applications, or maybe you know you want to go into a certain industry like real estate or something like that. Well, guess what? These are part and parcel of how that is done at a high level now, right? But sometimes you might need that kind of conversation piece to get you a point, and then quite frankly to help me scope it for you of what I think is actually feasible in 6 or 7 weeks of dedicated work, right? After the midterm, the reading load will drop significantly, and basically we'll look at applied versions of these things moving forward. FIST to 5 means like the reading load is really easy. It's the lowest I have in all my classes, and FIST being like it's the most reading or the most content to get through in all my classes. Where are we at? Okay, so this 1 means it's a heavy workload. Okay. Is that, so this is more, you're having to cover more concepts and more work outside of class for this class and other classes? Okay, yeah, that's fair. It's good for me to know, right?
Preparation-wise, at least.
Preparation? Yeah, because everything that I'm hitting you with is like new. Even if it's like, I know what a camera is, and then we're like, or I know what a human eye is, and it's like, what's acuity? And you're like, that's something, and I see you flipping through notes. I'll make some like study guides and stuff for the midterms with a lot of the terminology. And make no mistake, if you come to my office hours before the midterm and we sit down and talk through questions, it might be like a practice midterm for you, right? So if you're somebody who's got some anxiety about how you'll be able to perform in the moment communicating these concepts, I would highly encourage you to maybe try it out beforehand. The midterm, both presentation and oral exam is coming up quicker than you think. That make sense? Preamble out of the way, let's get started. So yeah, this week we're going to cover low level and mid vision. Oh, this is the other clicker that does this. I lost my other clicker. And we're going to start with some really simple concepts, and by the end of this week, we're going to build them into getting towards some of the things you did in that second Google Colab notebook where you did like a person detector. So let's jump right into it. I wanted to show this. This is the company NVIDIA, who we've probably all heard of. This is a general adversarial network. And what's going on here is that none of these are real people. This is a large deep learning model that is like randomly interpolating people. So it's using the last face to interpolate a new face, right? In an age of Sora and like text-to-vision systems, we know that deep learning has this capability. They're all very photogenic because it's trained on a data set of celebrities, which I find interesting in some ways. Kind of creepy, right? A little bit. What do we think about this?
I feel like I'm recognizing someone, but like also not.
Yeah, because they're not actually real people.
I know.
It's just randomly interpolating pixel values to give you a face, and it's doing it, it's kind of morphing from one feature, one face to another. Of course, this is, somewhat similar to what happens when you might text to image. Has anybody tried this with like a GPT, made a photo with a GPT?
Oh, yeah.
Yeah, so this is I think what we would consider to be high level computer vision or deep learning that is the kind of thing that's at your fingertips with a phone now. Any like ethical qualms about this? Does this excite people, make people nervous? What's going on here?
It just looks fun.
It looks funny, but you can think some applications that might be not as trippy and maybe not as funny.
Makes me a little bit uncomfortable.
Why?
It's creepy.
It's creepy?
I think like it is a little creepy, like the smiles and stuff, but also like my brain is just like it's freaking out my brain.
Yeah. Could I conceivably in today's era like create a nice video of you doing something you never did?
Yes.
Yeah, absolutely, right? This whole idea of deepfakes. And a lot of times when we get to high level computer vision or like transformer networks, like the big AI, we start to then have these questions like we did all the way back in week one, like what is consciousness, what is intelligence? Remember I showed the Claude example of the funeral. And maybe today we'll start to push back on this concept of intelligence a lot because we'll see that even though something like this can seem like, how is a computer doing this? We're going to start at the most basic level and begin to see how these things happen. So this is definitely a case of high level computer vision. This is another example from last lecture. This would be, I think, high level, right? Being able to say that that is a rifle, and I think there's a 94% chance it's a rifle. We're coming at like a semantic understanding of the image, right? It's not just pixels. We're able to group these features together and say, that's a dog, this is a cat, you're wearing a hat, and he's shooting a rifle, right?
Was for the segmentation Google Colab thing, was that based on like 94% chance? Like that was, because I remember for my picture it was like there was like 100% chance that was a chair. Was that like?
Yep.
Was that visibility or was that just chance?
Confidence interval.
Confidence.
It is 100% sure. 94% sure. It says you made a segmentation mask around, and it's gonna, I don't just like dancing, right? Like it's gonna say that it's 86% sure that that is a human. But maybe if it's like this, it will be 90% sure, right? And that's a reflection on what it's been trained on. Probably more humans in a more natural pose than something like that. All right. Image segmentation, right? Another example of high-level vision. And these high-level vision systems are building on everything we've covered so far and everything we're going to cover today. So we have low-level operations of computer vision that are working on pixels. Mid-level vision is typically where then we'll group those pixels together and try to like extract some meaningful features from the image. So one thing we might be doing that you might do a lot with AI or Photoshop is where you mask an image. You say, oh, I want that orange, but just the orange because I want to take that orange and put it somewhere else. We actually saw how to do that with hue, saturation, and value occasionally. And then high level is a semantic understanding of the image, right? I am 99% sure this is water. I'm 94% sure that's a person. And this is starting to get at something that classically we could consider to be somewhat intelligent, right? And so how do you build these intelligent systems out of things that are operating on the pixel? Well, that's a large part of what we'll explore this week. Am I moving too fast or we good? All right. So at the most basic level, a lot of what we're going to cover and a lot of what neural networks do is they create these filters, right? And these filters form a new image based on the way that the filter passes over all the pixels in the image. And why do we use filters? For a ton of applications. It could be for deep learning and convolutional neural networks, but it could also just be to blur an image or enhance an image or even resize an image. They're all these forms of filters. So you can envision a bunch of pixels and you're just going to go right over. And we have an example of blurring in the top left and then something called a histogram of gradients, which we'll cover later, either today or on Thursday. So filters are kind of the key to everything. And low level and mid level and traditional kind of applications of digital culture for computer vision, the human designs the filter, right? They decide what the filter is going to do. And really one of the foundational differences between deep learning and big AI is that the network decides what the filter is going to be. That's the classical difference there. So how do we make a filter? A fair question, one might ask. Well, we do it by first understanding, once again as a review, what an image is. And I'm going to use a lot of grayscale images here just because I don't want us to have to worry about multi-dimensional space. It's going to be simpler to just do everything in grayscale. So we can remember that the digital image is a matrix of light, right? What do I mean by that? They all have value. And what are what are those values mean? Keep talking.
Dark or no light, and 255 is light.
Yeah, and sometimes we normalize it between 0 and 1 just because we're not computers, that's easier. Dallin, what were you going to say?
Yeah, just the higher the number, the closer to white it is.
Yeah. Absolutely. And just one other content check. If we weren't doing it in a grayscale image and we're doing it in a color image, how many of these matrices would we have? We'd have 3. And then on the blue channel, that would just be blue light, turning the dial up and down. Ned, did you have something to add?
No, I was actually just going to bring up what you were saying.
Okay.
Like color imaging, it's like 3D.
Yeah, and if we looked at some applications where we collect spectrums of light that we can't see, like near infrared, infrared, types of ultraviolet, we could have actually a quote-unquote image that has a ton of different bands or kind of matrices. So how do we make a filter? It's all about a kernel. Not this kind of kernel, but that kind of kernel. This like small box that is going to move over the image, and at every one of those pixel values, it's going to apply this kernel to that value or its neighbors around it and calculate a new number. Does that make sense? Yeah. This is just an example of what this looks like. This is a Laplacian kernel, which is a type of edge detector. So it should be pulling out all the edges in the image. We're going to cover exactly what an edge is ad nauseum today. But you see how it works, right? The kernel is sliding over the image, is then doing that calculation for that very narrow patch, and then it's outputting a new image. It's a filter. It's a Laplacian filter, which is huge for building block of many types of more complicated systems. Fist 5, 5 means I'm feeling good. This is not too tough. Okay, I'm going to keep doing this today because we're going to take these simple concepts and just build on top of them to get to something towards the end that's a little more complicated. Yes?
So different kernels do different stuff.
Yes, 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 absolutely. And building kernels, traditionally humans did it, and now sometimes we just give a big neural network a bunch of examples of what we want, training data, and then we tell it, build a kernel. I'm trying to curse less. Is it working? Who knows? But I just caught myself there, so I think that's pretty good. I've got little nieces, and they're old enough that their cool uncle is dropping way too many. I think I'm a cool uncle. I'm dropping way too many curse words, so trying to cut down on that. All right, so here are some common kernels in computer vision. And you can see kind of what the kernel does, or what the numbers in the kernel, and then the output on the image as we go through. And maybe I should have made this bigger. The first one's an identity kernel, and it doesn't do anything. And you could think, why the heck, why the heck would you need this? Well, we'll look at some examples where the identity kernel is important, yeah.
Do you want to know every single type of kernel? Do we need to know like?
No.
Okay.
The ones that are like big on these slides are big, and I'm really big on teaching the theory and not having you do the math, because we're not in a math or computer science class. So I might say, hey, talk me through what blurring an image would look like, and what can we do with a blurred image that's important. And if you could explain, I'm never going to be like, tell me what's in that kernel.
Okay.
Does that make sense? Yeah, that's an excellent question. Questions like that, I think, are fantastic for us to know what's expected. So yeah, we have a couple different edge detectors. This one sharpens. This is a cool like embossing filter that makes something look kind of 3D even though it's not. All right. Feeling pretty good? Yeah.
I got a question. So is this just basically like a sliding window sort of, and there's like a multiplier based on?
That's exactly what it is. And I even have a slide about that. And it's next. So yeah, what are we doing with this kernel? We're sliding it over the image. We call this a convolution in like machine learning and computer vision and digital culture. Technically, it's not a convolution though. That's a misnomer. And it's not accurate. Technically, it's a cross correlation. A convolution would be that you take that kernel, you flip it on its side and go. But for whatever reason, somebody called it a convolution. We just call it a convolution. I just need to point that out so you can make like nerdy points at parties and look really cool in front of all your friends at the circle. It's technically not a convolution. It's a cross correlation. But we call it a convolution, right? It's just a quirk. Yeah, you should try that out this weekend, right? Yes.
Smoke-filled room.
Convolution, that kernel, we flip it on its side and then we go.
Why do you flip it?
Because that's what a convolution is. But in computer vision, we do a cross correlation. We just call it a convolution. So we're not flipping the kernel. And you see, kernel is not rotated, correlation, kernel is rotated. And then this is like, for you, Jabal, this is how we notate that in like a linear algebraic system.
Why would you rotate the kernel? What would that?
I don't do signal processing, but that would be an excellent question to ask somebody like Professor Rennie.
So it did not flip for the correlation, but it.
Yeah. That's technically what we're doing. We call it convolution. Like when we say a convolutional neural network, a CNN, which we'll cover in a couple weeks. I think for the majority of us, just it doesn't really matter. For those that are asking detailed questions, is because you're in linear algebra right now, I would think. All right, so what's a really simple use case for these kind of kernels? It could be resizing an image, right? So we have these zebras. The zebras are fantastic, and we're trying to resize or zoom in on this really small portion of the flank or the butt, and you'll see that different kernels give you different results, right? So some you have a better kind of maybe like bicubic interpolation kernel, and we have a lot of different ways of resizing images. We're not going to cover this in class. Just know that it's a kernel that does it, and it does it with some of these algorithms here. And this is like, what I've done here is like radically resized an image so you can see that there's kind of a no free lunch. Like you interject noise, right? It's not perfect. Still feeling good? Cool.
Wait,
So, yeah.
before we move on, when you say interject noise, I remember like that's a thing that I remember seeing like with the lab and everything.
Mhm.
Like give me like on layman's terms, like what you really mean by that.
Yeah, so if the idea is that we have a kernel, the kernel is sliding over the image. I'm just going to use sliding, right? That in that kernel, at every point in which it slides, it's doing a calculation where you're fundamentally changing those pixel values. And a lot of these calculations revolve around kind of calculating the nearest neighbors. And clearly, if you had one pixel that's 0, totally off, and one I'm going to use instead of 0 to 2 to 5, 0 to 1, and you average those weights, you now get 0.5, right? That's a blur.
Correct.
Does that make sense?
Yeah.
So let's actually talk about blurring, because blurring is simple, complicated, and really amazing. So you might think, why would anybody want to blur an image? Isn't the whole idea when we covered apertures and the camera model, wasn't the whole thing to make images that look good and not blurred? Didn't we develop like all these crazy systems of eyes to have more visual acuity? Why would you be doing this? Well, we're going to see that it's actually pretty fundamental to a lot of edge detection and a lot of these medium and high levels with some very cool little bit of math, a lot of common sense. So this is a drone orthomosaic that a team that I'm affiliated with took right after a hurricane or a typhoon in Quinhag, and we're assessing damage to infrastructure. And a lot of the models we use secretly behind the scenes actually blur the image a little bit. And by the end of at least this week, we'll understand fundamentally how we can make large maps or panoramas by stitching images together, because it's a classic low-medium computer vision problem. So we got original image, light blur, medium blur, and heavy blur. They may have any questions about that, which I think is very simple. It gets more blurry. Okay. And I will say that there is a value associated with it. And we're going to come back to that in just a second. All right, so just to review, because we're going to jump into something that's new. We have our good old friend, the matrix of light. We understand those values. And before we jump forward, we talked a lot in this class, especially last week, about an image as a function, right? An image of a function that takes 3D space and projects it onto a 2D plane, right? Does that make sense? If you're tired, you can stand up. I have no problem with that. You're a student athlete, so you're probably up pretty early in the morning lifting and stuff. No shame in that game. All right. 3D real world space projected onto a 2D plane, right? Take a look right here. We have like an X and Y coordinate. This is two-dimensional space. Is there a way that we could visualize it in three-dimensional space? And if we could, what would be the Z value or the height value? Is there a way that we could do this? Take this data here. It's in 2 dimensions. How could we potentially visualize it in 3? Our X and Y would probably stay the same, right? It would be the pixel location. What would the Z value be? The depth value, huh?
Getting like a depth value.
Mm-hmm. Yeah. If we were to reproject this into 3-dimensional space, what would our Z values be? This is like good old critical thinking. Hoping for somebody from the
Maybe.
Keep talking, because you're right.
I mean, it's the light is measured within each pixel.
Mm-hmm.
Z
Yeah, we could do that. We could make a three-dimensional representation of that image in which our X and Y aren't changed, but the Z values now are those pixel intensities. Do we get that? Is that hard to understand? It might not even really look like the image. I mean, technically it is. This area over here, that's your sky, and then when we look at the buoy, we have a lot of like changes in pixel intensity, which you're seeing here. Does that make sense?
Yeah.
Hard to think about how you could do that, but then once you see it, you're like, ah, okay.
We've seen that before, right? Like,
You've seen the picture of the buoy. I don't think we've looked at this. Yeah, this is new, because we're going to deal with this a lot today. Does that make sense, Dallin?
So,
You feeling it, Hayden?
so the Z value is what? It's the intensity. It's the intensity.
Intensities.
Okay.
Okay? Does that make sense?
What about different colors and absorbing the light? Like, does that not come out in the image since it's mapped to two dimensions first? Because you think like
Oh.
maybe a
Do you mean like if we had red, green, and blue channels?
if you have a darker image, a darker color and like a lighter color, would that not, since it's mapped to two dimensions, since those are technically absorbing light differently?
This is not like the reflectance, all that stuff is already baked into the image itself, right? That's what was reflected onto or absorbed by the sensor. Does that make sense? So then we are just projecting that straight into 3 dimensions. It's another way of looking at the data and projecting it from 2D to 3D, which is like a lot of machine learning involves projecting things into higher dimensions or scaling them down. Principal components analysis, PCA, is like a very good example of that, right? You're looking very astute. Does this make sense? Or okay, good. So yeah, surface height of this 3D model is the pixel intensity at a given position. All right, let's get into it then. So what are we doing when we're smoothing an image? Well, we're applying that kernel, and we're doing that kind of weighted sum over the entire thing, and we're getting rid of all these little bumps, right? You can see these like little bumps here and there, and after we're smoothing, we're kind of making a flatter 3D surface. Cool? Interesting? Yeah, I think so. I spent way too much time making these GIFs. I woke up at like 5 in the morning this morning to realize I wanted to make another GIF. It's not good for me. Yes?
Why do we need to smooth it? Isn't like a raw image better?
Hold that thought, because I'm going to show you a way that you can even just basically use blurred images to make an edge detector. But yes, there are many reasons why we have to smooth. Yeah.
When you say you multiply like the weighted sum, so you're taking each one of those intensities and doing the 1/9 for each one?
Yep. Your kernel, it might be 2 pixels by 2 pixels. So you're like averaging those values within it, computing the weighted sum, that's your new pixel value, right? Which is why it's literally sliding over the box, and that box is roughly how big the kernel is. You can make like a 3x3, a 9x9 kernel. Generally, even-sized kernels don't work well for some mathematical reasons. But yeah, the size of the kernel is important, and then what goes inside the kernel is important. And this is hitting every pixel, and it's calculating new value, but it's calculating that value based on the size of the window around it. Does that make sense? Which is why it's like a function of linear algebra, right? Because we're dealing with like a big matrix and then sliding small ones over.
Is it a convolution or is it just a sliding window?
It's a sliding window. Technically, it's cross correlation, but we call it a convolution. I should not have put that slide in there. But does that make sense? We're just gonna call it sliding window, right? But in like physics, you like Dr. Holt would be like that's not a convolution, and you have to say, Dr. Holt, I know you're right. It's just these dumb people just call it a convolution. But I'll call it a sliding window. Okay, cool. So you might be thinking, maybe you are, maybe you're not. I want to see what that actually looks like in 3D space, right? And Gaussian blurs are another type of blurring that we can do that are, they're a little different than just that box blur, right? Instead of dividing by like a set ratio, we use a normalized distribution. If you ever took stats, like a bell curve, that's a Gaussian curve. And so we're calculating some standard deviation. If we took that 3D kind of look of the Gaussian curve and took a 2D view of it, that's what that looks like, and that's literally kind of what the kernel is doing as it's sliding over. So Gaussians are a fantastic way to blur images. I don't know why theoretically that's the case, and I don't know if anybody knows. It's just one of these things. I'm sure somebody smarter than me could give me a theoretical reason for it, but a lot of folks will just say, yeah, they work. They work pretty well. So on the right, we have now the exact same thing happening. We're going to use a Gaussian blur to smooth this image. We'll see that it smooths a little different because it's doing this weighted sum based on a normal distribution. So a little bit of stats, a little bit of images, a little bit of 3D projection, tiny bit of linear algebra, kind of bringing it all together. You don't need to be fluent in any of these things. But if you are, it just makes it, I think, a little more fascinating. Show of hands, how many people have taken algebra at some point in their life? I would hope so. Your public school systems have not failed you. Pre-calc, show of hands. Yeah. Trig? Excellent. Also high school. Maybe, maybe not. Calculus here. Okay, fair amount. Linear algebra. 2. Okay. Kind of, sort of?
Pretty sure I took that in high school.
Okay. Yeah, right on. So yeah, let's just look at the difference between these. They're pretty similar, but they're a little different too. Okay. So we now know how to blur an image. Yes. I'm very happy with that. That's a pretty good win for today. But we got to do a lot more. And this is specifically to your question, Ashford. Why do we blur? Well, we can minimize noise, right? There might be a lot of features in the image that we don't actually care about. We're building a drone detector, right? All of these rocks, not important. We're looking for the drone. We're looking for the biggest features in the image. The other reason that we can, and we do that for feature extraction to reduce false positives. And we also use it in deep learning a lot of times that you'll blur the image before you put it in a neural network. But we can also extract features from blurs, which is cool, or edges from blurs, which is really, really cool. And remember, all these slides are always posted up, and the videos are posted as well. So I said we can detect edges, and I gave you an example of a Laplacian that's calculating an edge. You saw what an edge looks like when we do it. So let's think about, well, what is an edge? What do we think an edge is? I gave you that 3D model, yeah.
Like the difference in the value, like next to each other.
Yeah. And on the 2D plane, it's very easy to see, right? If I make a strong edge like 0 and 255, oh, that's an edge. In the 3D space that we looked at, what would an edge be?
Distance between.
Not distance between, it would be a big like trough or big,
Just drop.
yeah, big drop. Yeah. And for those that have been in pre-calc or calc, you can probably do that by calculating the derivative, right? And so, we talk about slope in a linear function, rise over run, and then we have this whole branch of mathematics that tries to do that with curves, right? Calculus. For those that maybe aren't super familiar with derivatives, derivatives tell you the change of slope on a curve or where on a curve you are, right? And then the second derivative tells you kind of like in what direction you're heading. That's a very reductionist account of it, but it allows you to go to a curve and see where you are at that point and see if you're heading up and down. So a real world example that's often used is like, I'm at mile marker 50 versus I'm going 60 miles an hour versus I'm speeding up or slowing down. So take that image, we put it into 3D space, and now our edges in the image are going to be these places where there are just steep drop-offs. And we can probably calculate that with derivatives, which is cool. And that's exactly what we see, right? When we're building an edge detection kernel, what we are trying to do is get a strong derivative or calculate derivatives and find very rapid changes in slope, or very rapid changes in that z dimension. And so I've kind of reprojected parts of this right here back into 2D planes, so you can see, oh yeah, absolutely, we got sharp drop-offs. We probably have an edge there. And then what we really need to do is figure out which edges are important and how can we combine edges together to come to a sense of something called a feature, like a person or chair, and then how can we reliably always predict that feature. Good? Fist 5, 5, I'm chilling, this is good. Fist is, I'm starting to get a little confused. Okay, so we dropped from a 5 to a 3 for Ned and Ashford. How can I help?
I think I understand. I'm just like, I can't honestly put up a 5. Like,
Yeah.
If you ask me
It's
to-
starting to get complicated. Yeah.
Like, I mean, I'm starting to get it a little.
Yeah. I'm trying to break it down because for a lot of this stuff, like I have had a lot of trouble understanding myself, so I'm always trying to give you just like little pieces that are bite-sized and then put it together with a lot of graphs. Okay, so one way that we could blur an image and start to get to an edge detector is the Laplacian, which looks a lot like a Gaussian blur, right? And this is the Laplacian kernel. And what it's going to do is go ahead and move through that image just like we saw earlier and hit our edges. Now this is where I think blurring, some people call it the sombrero filter because it kind of looks like a sombrero. And this is how that filter convolutes over. And the edges basically are given to us as positive changes. So then we can find those periods of rapid change in intensity and then get us an image that just has those things, right? Classic edge detector. You can also do it just with variations of blur in an image. So, and this is kind of crazy to me. So if you took a couple different Gaussian blurs of an image at different levels of blur, when you subtract those from the original image, you'll get the edges on that image. And this kind of shows us how that is, right? So like the Laplacian, it's kind of this inverted hat, and the narrow Gaussian preserves the edges in one direction, and then when we subtract them, we get our edges. So kind of cool. We can do an edge detector just from blurring images, which is interesting. We're going to kind of gloss over this and move forward. But if you're interested in like specifically how that works, I'm happy to give you some, give you a Google Colab where you can do it yourself. So another way we could detect edges is by something called a Sobel filter, where we calculate the gradient on just, this is moving a little too fast. I'm going to slow this down next time I teach this class. Yeah, way too fast. But the Sobel filter is going to first go through just in the x direction and then in the y direction. And then basically multiply those two things together, and you'll get the vertical edges and the horizontal edges. You put those together, and you got a good magnitude of your edges. And you see that they're a little different, right? There are a lot of different ways that we can get to what an edge is. And people for like 40 years, all they did was design different filters for edge detection. Does that make sense? So with the gradient in the x direction, the gradient in the y direction, boom, we have our edge filtering algorithm. Enter canny edge detection. And this is an important one because this is the first approach to digital images and digital culture and computer vision that I would consider to be like a straight up image processing pipeline, where there are many steps, the image goes through all of those steps, and at the end, we get a really nice edge detector algorithm. And a lot of the problems you might try to tackle in this class that you want to apply to images and digital culture are going to be probably image processing pipelines. You won't just be able to say, oh, I'm going to do this. Step 1 to step 2, I have this solution. We're going to take a series of incremental steps, yes?
How long would you say it would take a beginner in Python to like make something that just takes an image and
2 lines of code, a 5-minute YouTube tutorial. I mean, it's not hard, right? If you have the kernel, you could do it all in NumPy if you really wanted to. I don't know why you would, but I mean, you've got your image, you read that as a 2-dimensional matrix of light, and then you got your kernel and you slide it over, and you'll have a blurred image if you select the right kernel. Does that make sense?
Can you do it in Colab or does it need to?
Yeah, you can do it in Colab. Read the image in with PIL, right? Python Image Library, and then apply your filter to it, and then save your augmented matrix as a JPEG or a PNG or whatever. All right, so step 1, we're gonna blur it, and then we're gonna do some different gradients, just like the Sobel filter, and then some steps 4 through 5 are new to us, but one of those steps, non-max suppression, we're gonna see again and again and again. So the first step in candy edge detection is we're gonna blur that image. We are going to blur it. Blurring the image smooths any noise of like little features we don't want, but it still preserves like the big features that we need. This is a drone shot that I showed you earlier. It's just in grayscale now. And let's say that we're trying to do like a house detector, because I want to go through and I want to quickly be able to get the drone out of the drone dock, fly it over the village, and then say, this house has been damaged, this house has been damaged, this house has been damaged. Let's calculate the whole sum of the damage for a FEMA application, right? This would be like a classic use where I could think about using some low and mid-level computer vision to do it, or some deep learning. So first step, we blur the image. Any questions about that? Next, we run our Sobel filters over, yes?
What was the sigma value?
That is your blurring value. So like the higher the sigma, the more blur. Does that make sense?
So does that change the numbers in the kernel?
Yes, and we can talk about that later. Does that make sense? The next step is that you run that Sobel filter over it, so you're getting the gradient of edges in the X direction and the Y direction. Doesn't really look like a full-on account yet, but this is a pipeline, yes.
When you talk about gradient, are you talking about like the contours, like if you're like cutting it or cutting the 3D image in half, sort of, and then
Pretend this is 3-dimensional space. Strong gradient change.
yeah.
And then if I project it into 2D, let's just say like, strong gradient flux.
Yeah.
Does that make sense?
Yeah.
So we're doing it in the X direction and then the Y direction.
Yeah. Okay.
Does that make sense? All right. So the next thing we do is we calculate the magnitude and direction. And for those of us that aren't math inclined, we don't have to worry about Y, but we're like squaring it and taking the root to like normalize it basically for the magnitude. So we do just a little bit of math on top of the Sobel filter. And yeah, it's starting to come together to look like an edge, right? Cool. What is one thing we might need to pay attention to or worry about if we're predicting edges this way? Well, it could be that you don't want the edges that are really thick to outweigh the ones that are really small, right? And so we're going to do something called non-max suppression, which is going to thin the edges, and that way we get like a nice clear pixel in which each edge is like 1 pixel wide, right? So we apply a function over what we've got, and that is going to allow us to have a kind of normalized distribution of the edges so that we don't get, like if there's one big edge, it doesn't throw off the algorithm basically. And non-max suppression is important, and we'll talk about it for a couple slides because we do this so much with like a lot of AI. Yes?
Is that non-max suppression, is it done with like a different kernel or something?
We're going to hop into non-max suppression in a couple slides. If you still have that question, let's talk about it after class. And then we basically classify each edge as strong, weak, or not an edge. So we classify it a little bit. All right, this is like a 1,000-yard overview of edge detection, and we can jump into it for those that think they want to build one. We'll jump into it and get a lot more in detail. And then the last part, once we've classified them, is we just keep the strong edges. We throw out the ones that are not strong.
What is a strong edge? With higher gradient?
Like, don't worry about the math quite yet. Like, look at what the picture looks like, right? We're keeping the edges that are strong, that are continuous and strong. And we'll talk about this when we talk about corners in a little bit too. So then we only keep the edges if they connect to other strong edges. This is called skeletonization a lot of times. It's like, I know this is good, but what's good around it? If it continues to be good, let's keep it. If it dips off, then let's not, right? That way we're throwing out edges that might just be changes in illumination. They could be like noise that we're not super interested in, like the little pebbles around the drone, that kind of thing. So non-max suppression is pretty important for a lot of deep learning. And the idea here is that we want to only keep the strongest results of the algorithm, the ones that are most predictive. So if we're going to look at your prediction, your little kernel or your edge detector, look at your prediction and your prediction and your prediction, and then we're going to just keep the one that is the best. I think this, like, let's not talk about it in text. Let's like look at it in terms of what this looks like in 2 dimensions, right? So we have a lot of different ones, a lot of different responses, and we just want to keep the ones that are at the top of the curve, right? And there should be one probably over here as well. That's what non-max suppression is doing, right? And if you're taking some calculus, you can start to think, okay, how would I do this? That kind of thing. Let's look at, for those that aren't math inclined, let's look at kind of a visual depiction, right? And so we have this gradient, we have the edge, and we have a gradient direction on either side as the edge begins to appear or begins to disappear. You can think about that in the 2-dimensional space, the 0 to 2 to 5, or the 3-dimensional space. And basically what we're trying to do is just keep that center line, keep the maximum return. If both those things aren't super helpful to you, let's look at an actual example, right? And you can see exactly what's happening on here. We're just keeping where the response is the strongest on the gradient. Does that help? All right. Once again, if none of this is your thing, let's look at an example of this in deep learning, right? And so this is like you're training that rifle detector and it's not doing a good job. You know you're going to have to give it more training data. And it's doing a bunch of predictions. We just tell it, keep the one that is most accurate, right? And in this case, I'd probably be like, man, I need to put a lot more training data into this algorithm because it's not really hitting the rifle, is it? Right? So this is used a lot in object detection, is that way you don't get like 50 cats when there's only one cat, because it takes 3/4 of the cat and says it's a cat, and 1/4, and then the whole cat. We just look around and see where the other bounding boxes are, and we say, let's keep the one that seems to be the strongest. Does that make sense? Really technical term, right? Non-max suppression. Oh God, it has to do with derivatives and it's not that complicated. So non-max suppression finds the local maxima, the period or the point where there's the highest degree of change, and it just basically cuts everything out, suppresses everything. As a function, it returns 0 for things that aren't in the maximum. Does that make sense mathematically?
So what would be the distance away from the max that would make it a different maximum?
Yeah, if you know what I mean. Yeah, so you're thinking about the graph there. Like that's kind of up to you or the algorithm to decide like the neighbors around you which you want to compare. Does that make sense? It does make sense?
Yeah.
Good. So yeah, keep the best response and get rid of everything else. And you see it in everything. Canny edge detection, YOLO, faster RCNN. You ran RCNN when you did the people detector, right? And it didn't give you a bunch of different segmentation masks, it gave you one because it was doing some non-max suppression. And in a neural network, that's usually a step in the process. Yes, Ashford.
What's the next step after the Gaussian blur?
Yep, in the X and Y directions, right? And then we calculate the magnitude and gradient from that subwheel filter, non-max suppression, thresholding, and then basically keep the things that are good. All right, so yeah, I try to bring in like real world cases from some of the work that I do. Again, this gives you a good example of what a UPIC village looks like from the top-down perspective. But let's say we have this big old drone photo. We want to make like a big old map. We want to run this algorithm not just on a photo, but like the entire space, right? I want to map all of Hampden-Sydney, have one giant image, one giant map, and then do a people detector. Or see how the progress in Kirby is going over time, right? These are all ways that we apply this to make a lot of money these days. So once again, just showing you a couple of the different edge detection algorithms we've covered, so you can see that they give different results, right? Not surprising, no free lunch, right? You decide to do it one way, there are some benefits and some drawbacks as well. The other thing, and this is kind of an aside, but once you have the edges, you can actually sharpen images by taking the original image and subtracting it from. So that's, this is a sharpening kernel. You see how it makes a sharper image? And this is cool too, because Jabal, you had, I think, asked, do we make these? How do we make these? One thing that you learn from just a simple image sharpening kernel, this is the kernel on the far left. You could do this a number of ways. You could have two kernels that you apply back to back, or you could use the associative property in mathematics to just combine them together, right? So that, I think that's kind of cool. And so a sharpened kernel can be just, you apply just this kernel to it and you get your sharpened image, or using the associative property, we could do two different things. We could do the Gaussian and then an edge.
Is
Yeah.
Kenny Edge a neural network in some sense?
No, it is not a neural network. It's a traditional image processing pipeline.
But isn't neural networks like connections of different kernels at some?
The difference being that there is like a linear flow through the algorithm, right? The difference being in a neural network, you don't control what the filters are. The filters are generally built based on the training data set. That's what makes it like an intelligent system. So yeah, you can't go back and be like, oh yeah, I definitely used a sharpening kernel at that step. Instead, you like throw it in there and you get to decide how many neurons, you get to decide some things about non-max suppression, what the activation function is on, but then it basically says, I can do it now. Does that make sense? Yeah, so yeah, if we take two kernels over an image, then we can take like a Laplacian and an identity kernel, but if we add those together, we get our sharpened kernel, which I think is cool and interesting, and also the associative property of mathematics.
You said that you subtract the blur from the original image to sharpen it?
Yes.
You did the edges and then you
Yeah.
subtract that.
Mhm.
Okay.
Yeah, so it's the details is the original minus blurred, or the original plus the sharpened kernel. So edges are great, love edges, but they might not actually, you might not be able to do a lot of inference based on just a series of edges, right? It's hard to look at anything that we looked at already and be like, oh yeah, it'd be really easy to see how I could take some of those edges and say that's a house. We might actually need a corner. Anybody know what a corner is? Where two edges come together. I do this not like to mess with your mind, but sometimes like I know we're talking about high level stuff, but it's really not that complicated, right? A corner is a place where two edges come together, right? So this could be a flat region, right, where there's like just no response. This is a strong edge where we have a gradient change, and then a corner is a place where they come together. Hey, cool. Why is this important? Well, in a flat region, you can slide your kernel all over the place. You're not going to get any change, right? There's no edge. Here, if you slide in this direction, you'll get a change, but you won't get any change if you slide up and down. Well, that might be hard. Corners, you're always going to get a change if you change the position of the kernel. So sometimes, yeah, so edges versus corners, great. We've detected a bunch of edges, but they're not going to help us that much. We need to put them together. We need to take those edges and put them together into larger features. This is this is called aperture problem. It's exactly what I mentioned. Like, these three kernels are in very different places in the image, but they're giving the same response because they're calculating the gradient there. Which is annoying. Why we got to use corners, because corners are get better. So just a quick summary here. Edges, it's in one direction. It can slide along the edge, but not much else. And you could calculate it with a first derivative or a Sobel filter, but you're not going to be able to put it together in any ways. And if we put them together and we had a corner detector, now we might actually be able to do things like match images. I could take a picture of you and then another picture of you and start to match those things together. So that's what corner detection looks like in practice. This is a Harris corner detector, one of the original ones and more famous one. And you see that it's not pulling out all the edges, it's just showing you where two edges come together with a strong response. So the first thing we're going to do, run our good old-fashioned Sobel filters over it, get our X and Y gradients of edges. This should be not too surprising and a bit of a review now. The next thing, and technically we could use a lot of different types of kernels to get our edges, but Sobels are quick, so we use a Sobel, but we could use like a Schar filter. So we're going to get our edges. That's awesome. And the X and Y directions. And then we're going to basically put them, just like the image is a matrix of light, we'll put them in a very small matrix, right? And if you're not mathematically inclined, just tune out for 30 seconds, right? But we're basically going to make a little tiny matrix, just like the image, but it'll have those magnitudes.
Should it only be a 2x? Or could you do it like a 3x?
Yeah, let's talk about that after class. That makes sense. And then quick like crash course. The way that we're going to do Harris corner detection has to do with something called eigenvalues and eigenvectors. I thought the first time I came across this, I was like, I can never do this. I'm not smart enough. But it's actually very simple, right? Eigenvalues, these are both, we have two vectors, X and Y direction. And if we were to do something like this, where we flip the image, we have preserved the eigenvectors. They haven't really changed, right? They haven't come off that axis. Does that make sense? Now, if we did something like shear the image, we have changed. This is no longer an eigenvector because we've changed its direction, but the x direction is still the same. Does that make sense? Eigen means like particular in German, so that's just literally all it translates. Unique, if you will. So if we stretch it, have we changed the eigenvectors? You're saying no, why? Exactly. Yeah, exactly. So we're going to go ahead and make that, that small tensor of our Sobel filters, right? And then we're going to calculate the eigenvectors for it. And we don't have to worry about how we do that. We just know that we do that. We're going to calculate the eigenvalues, which is basically a thing you can multiply against your eigenvector to stretch out the line but not change the direction of it. Does that make sense? If you're not mathematically inclined, welcome back to the lecture. These are basically measuring intensity change. And this is how we're going to get a corner. Because we get two eigenvalues, and in a flat region, there's really no response. In an edge, there'll be a response on one but not the other. And in a corner, we'll get a strong response on both eigenvalues. I really did a disservice to eigenvectors and eigenvalues there, but I think I did a crash course. And so kind of like the decision. We're looking for a high response on both of these. If we get the high response, we have a corner. If we get nothing, it's not an edge. And if we get in one direction, it's an edge and not a corner. Does that make sense? Fist 5, where are we at? This is like the toughest stuff we're going to do today in terms of like theoretical math. 3, 3, 0. That's fine. That is absolutely fine. All right. Cool. So one thing that's cool about the Harris corner, they found a shortcut around doing all that we just talked about. We don't need to really spend too much time about it, but they found an approximation for eigenvalues, which is cool. And why does this work? Again, because if you have those two big responses where two edges come together, you have a corner. If you take anything away from this, is like corners are where two edges come together. You're like, why did we spend 20 minutes talking about that? I knew that already. So once again, now we can begin to understand how we detect corners. Now you might say, God, that is theoretically maybe interesting, but how do we use that? Well, here's a place where we use it. Here's a place where your phone uses it all the time, image stitching. So this is a pretty nice image. It has a lot of features that we could classify as corners. What if I told you this was not one image, but it was a series of two images put together, right? Because we could match those corners. Hey, that's kind of cool, right? Yeah, so like we can make panoramas, we can take big pictures. I know it doesn't seem like what we looked at with the celebrity face detector, but we're starting to do some things that are a little different, right? Yeah, that's cool. So we detect our key points or our corners, and then we match them. Pretty simple. So we got like 147 key points, awesome, and we start matching them together. So now we can make big pictures out of little pictures. What do you think we need, though, in order to do that? Well, yeah, there could be some blur, right, in there. There probably needs to be some overlap between the two images. It might find corners, and they're not going to be real corners if I take a picture of this wall and then that wall, right? But if I took a picture here, 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 and here, as long as there is some overlap, I can begin to stitch. Yes?
To stitch them, do you need like the camera to be at the same like height, and you just like?
We're going to cover this probably on Thursday because it's already 11:10. But yeah, man.
Save it for Thursday.
No. Like we're going to talk about it right now, but it's going to be to correct for that is like a lot of more complicated things. But what you're showing me, Manning, is that you're understanding what we talked about in terms of the camera, and you're thinking about the position of the camera relative to the image plane, which is what this is all about. In fact, this pipeline of Harris detection and key point matching is fantastic, except that one, it's not scale invariant, right? If you take something exactly what you're talking about, if you take a picture off center, center, and center, or if the scale of the image, right? So those two images, one's blown up and one's shrunken, it's not going to be able to do it. It's also not really good with like a modern camera. You take out your iPhone, you take a picture, that exposure triangle, aperture, shutter length are changing constantly. So you could get different illumination values, and it could be the exact same image, right? But some of the pixels are slightly darker because a cloud came through and then your camera changed exposure values. It's not going to be good at that. The Harris corner detection is great for tying things together within like a very narrow window of application. That's very sensitive to noise, and it's not scale invariant. So this, you are on the nose, because this is exactly what we're starting to get at, right? We can have an image that I think is like the same image, or let's put it this way, it's capturing the same features, right? I think it's fair to say that like this, if we're talking about high level, this is a buoy, and we're going to look at a bunch of different pictures of buoys, but they're not all going to be represented the exact same way, right? So we know that like an image could be moved a little bit. That still seems pretty simple. But what if we then like did a Euclidean transform and we started to twist the image, right? You can think about doing that panorama, but you're not quite straight with the camera. Or if like we're trying to, some of the stuff like Andrew Winans would do, where he'd take a bunch of pictures and build a 3D model. That camera is all over the place when he's doing it, right? Is this starting to, yeah, and then you had a question, Ashford?
If we locked like all the values of the camera, and let's say the lighting didn't change, how would that affect the edge detection?
Well, on Harris corner detection, it wouldn't work, right? Because you'd have different responses in terms of pixels, and it's calculating those edges based on the pixel value. So there's something else we have to do to get to something that's illumination invariant and scale invariant. Like, I love this because from a human perspective, it's like very simple how you might be able to say, like, that's his hand and his hand's over here. But Harris corner detection is not going to be able to do that. Another thing we could do is like change basically everything, except the only thing that we keep the same are the angles of the image. There's a similarity. And then scaling, stretching it in or out, all going to be problems. Big problems. And then affine, which is like that gets specifically at the idea that we're looking at it from different angles. So all huge problems, and I love that you brought this up because you're anticipating, right? You're putting into theory, you're putting into practice what we've talked about. So somebody has to solve for this. Thankfully, it's not us. And then, another type of projective transform called homography, which is actually kind of the solution to this. So what do we do with this? The issue that Manning brought up. Ooh, we got like 6 minutes left. So, how much further? Actually, I'm going to stop here. We're over at 11:20, right? Yeah, we got 6 minutes. And before we jump into the second half of this, will be Thursday. I want to check where we're at. How do we feel so far? You're like.
I was more comfortable with like the first 40 minutes of the class.
Yeah.
And after that, I kind of got a little shaky.
Okay, what's shaky for you? Was it like all the math on the board?
I mean, you kind of just went like a little faster
Yeah,
in
yeah.
the second half of class, so I wasn't able to write as much down and get it all, but like it still like makes kind of sense to me. I would just need to go back over it like 1 or 2 more times to fully get it.
Big takeaways I think we want to get to here are that a lot of the complicated things that we might do in this class when you decide you want to build this system are going to be based around filters. Those filters slide over images, right? The idea that some of the features that we might be trying to extract work really well when we consider them as a three-dimensional problem and then calculate things like derivatives or change in slope, right? And exactly that is detecting an edge, right? And then edges are great, but we might need to put them together in corners where two edges come together. That is basically all we covered thus far. And on Thursday, we're going to keep running with that idea and then try to make an edge detector that will allow us to like stitch together a big map or a panorama, accounting for everything that you brought up, Manning, which is like, well, the camera is located in real world space around that thing we're trying to capture. So what happens if it's easy to see how if we did this and that, Harris might work if the lighting conditions are the same. But if we're doing this, can it work? And I'm telling you now, Harris can't do it. But we're going to look at a bunch of stuff on Thursday for solutions to this problem that are very related to what we covered last Tuesday in terms of the pinhole camera and rays of light hitting a sensor. Does that make sense? I will say that we're going to enter into a couple weeks of just like really theoretical stuff, and I totally understand if sometimes it feels like I'm